been waiting way too long. Yeah, I've been down here trying to get it. Yeah, I've been waiting way too long.
Here is the video for chapter 2.2, which is about conditional statements and also what we would call logic. So there are a lot of vocab words in here. Please make sure you write the definitions as well as extra notes on some of the explanations that I give. So the first word is a conditional statement. Conditional statement is a logical statement that has two parts. Those two parts are called the hypothesis and the conclusion. An example here is if a number is a whole number, then it is an integer. And this conditional statement is actually written in if-then form, which we'll talk about in just a second. But in this conditional statement, if a number is a whole number is the P, that's the hypothesis, and then it is an integer is the Q, which is the conclusion. So we use the letters P and Q to denote hypothesis and conclusion. So here we have some statements. These would be called conditional statements, but right now they are not in the if-then form, and we're going to rewrite them so that they would be in the if-then form. So statement A says all 90-degree angles are right angles. So in if-then form, I'm going to say, if the measure of an angle is 90 degrees, then it is a right angle. So in this conditional statement, specifically in the if-then form, the measure of an angle is 90 degrees, that's my P, and it is a right angle is my Q. So again, the hypothesis is the measure of an angle is 90 degrees, and the conclusion is it is a right angle. Our next statement says when n equals 9, n squared equals 81. So our conditional statement written in the if-then form is going to say if n equals 9, then n squared equals 81. Our hypothesis is n equals 9, and our conclusion is n squared equals 81. The negation of a statement is the opposite of the original statement. So that's a definition you need to know for negation. So here's three examples. Let's look at the negation. For the statement the ball is red, the negation of that would be the ball is not red. Not red is the opposite of red. The test is not long. The opposite of the test is not long is the test is long. So each of those in red is the negation of the statement in black. Just so you know, we use the notation like this, not P. So this means the negation of P. So if you see that symbol, that's what that means. All right, so now we're going to look at conditional statement and then also the converse, inverse, and contrapositive of that conditional statement. So our example here is if Mark lives in LA, then he lives in Southern California. In this conditional statement, Mark lives in LA is our hypothesis, and he lives in Southern California is our conclusion. So that's our P and our Q. So the conditional statement, that's what I gave you here. If P, then Q. That's how you read this. If P, then Q. Now the truth value of that, if the hypothesis is true and the conclusion is true, then the conditional is true. If the hypothesis is false, then it doesn't matter what the conclusion is, the truth value would actually still be true. But let's take a look at this. If Mark lives in LA, then he lives in Southern California. So that would be true. Assuming Mark lives in LA, then he will live in Southern California. The converse of this is if Q, then P, meaning you flip-flop the hypothesis and the conclusion. So if Mark lives in Southern California, then he lives in LA. Is that true? Not necessarily. There's a lot of other cities in Southern California, so that is false. The inverse is if not P, then not Q. That's what that means. If not P, then not Q. So if Mark does not live in LA, then he does not live in Southern California. So if he does not live in LA, then he does not live in, well, if he doesn't live in LA, then that means he could live in San Diego, but which means he still lives in Southern California. So this is false. The contrapositive is if not Q, then not P. And so this would be if he does not live in Southern California, then he does not live in LA, which is true. So what you will notice here is this, that the conditional and the contrapositive are logically equivalent. You need to write that down. This is always the case. The conditional and the contrapositive will always be logically equivalent, which means their truth value will be the same. So if one of them is true, the other one is true. If one of them is false, the other is false. Sometimes it's easier to figure out if the conditional is true or not by actually using the contrapositive. So again, because they have the same truth value, you could just look at one of them and determine the truth value. In the same way, the converse and the inverse are also logically equivalent. Now, it is possible that every single one of these could have the same truth value, but it will always be that the conditional and the contrapositive are the same and the converse and the inverse are the same in regards to their truth value. So that's why we call them logically equivalent. You need to have these definitions written down. Equivalent statements, that's what I just talked about. Statements that have the same truth value. Perpendicular lines are two lines that intersect to form a right angle. And a biconditional statement is used when the conditional and its converse are both true. And the language we use there is called if and only if. So we can write a biconditional statement if both of these, conditional and the converse, are true. So for this statement, we could not do that. But I'm going to show you an example where we can. So here is the definition of perpendicular lines written as a conditional statement in the if-then form. If two lines intersect to form a right angle, that is my P, then the lines are perpendicular, or then they're perpendicular lines. So let's think about the truth value of this. So is the conditional true? The conditional, yes, is true. That's the definition. If two lines intersect to form a right angle, then they are perpendicular lines. Is the converse true? Well, the converse is if two lines are perpendicular, then they intersect to form a right angle. Is that true? Yes, that is also true. So because these are both true, we could write this statement as two lines are perpendicular if and only if they intersect to form a right angle. That if and only if part is the part that makes it a biconditional kind of meaning both ways. So no matter which way, if you read it as if P then Q, and you also read it as if Q then P, it's the truth, it's true for both of those scenarios.
I've been waiting way too long.